Here in Washington, we have our own volcano threat in the Cascade Mountains, which on average erupts once or twice every century.
More numbers. 24 park rangers assisted in the mission on the mountain. It happened on the Liberty Ridge roof.
A powerful magma surge deep beneath some of the United States' most iconic and volatile geological landmarks, Yellowstone, Mount Rainier, and the Teton Range, has triggered a red alert from geologists monitoring subterranean activity. This sudden escalation, marked by abnormal seismic behavior and surging thermal energy, has captivated scientists and concerned observers alike. The red alert status is not issued lightly. It signifies a major increase in volcanic unrest and reflects a heightened potential for geological events that could reshape entire regions. Before we start, smash the like and subscribe buttons for more updates. At the heart of this dramatic alert is the Yellowstone caldera, a supervolcano that has fascinated and unnerved researchers for decades. Spanning parts of Wyoming, Montana, and Idaho, Yellowstone is known for its massive subterranean magma chamber, which has the potential to fuel cataclysmic eruptions. Recent data from ground-based instruments and satellite thermal imagery show a striking uptick in activity. Geologists have observed an influx of molten rock rising from the deeper mantle toward the surface, increasing pressure within the caldera's massive magma reservoir. Although it remains far below the eruption threshold, the movement of magma alone is enough to cause widespread changes in geothermal features, as well as increase the frequency and magnitude of earthquakes across the park. What sets this event apart from prior activity is the simultaneous upheaval detected beneath Mount Rainier and the Teton Range. Mount Rainier, a stratovolcano situated in Washington state, poses a different kind of risk due to its vast snow and ice cover. A magma surge in this area does not merely signal volcanic stirring. It dramatically elevates the threat of lahars, or volcanic mudflows. These deadly torrents can rush down valleys with little warning, erasing towns and infrastructure in minutes. The magma surge beneath Rainier has also been accompanied by swarms of shallow earthquakes and noticeable ground deformation. Satellite interferometry reveals slight but rapid bulging of the mountain's southern flank, indicating upward pressure that geologists had not expected so soon. In the Teton Range, which is not typically associated with volcanic eruptions, the appearance of a magma pulse presents a geological mystery and an unsettling variable. The Teton Fault, a major geological structure running beneath the range, is capable of producing devastating earthquakes. The sudden thermal anomaly detected there suggests the presence of deep crustal melting or the intrusion of magma into previously stable rock layers. This unexpected thermal activity has raised questions about the region's deeper geological dynamics. Scientists now face the possibility that the tectonic and magmatic systems beneath the Tetons are more interconnected with those under Yellowstone than previously assumed. The convergence of activity at all three locations suggests a broader mantle process at play. One leading hypothesis is that a regional mantle plume, long suspected to feed the Yellowstone hotspot, is now exhibiting intensified upwelling. A mantle plume is essentially a column of superheated rock rising from deep within Earth's mantle. When this plume interacts with the crust, it can form volcanic hotspots, cause massive melting, and alter tectonic behaviors. The idea that this plume could be influencing Mount Rainier and the Tetons introduces new questions about the spatial extent of the plume's influence and the timing of volcanic cycles in the broader region. What makes this situation especially tense is the unpredictability inherent in such dynamic systems. Geologists rely on models built on past behavior, yet volcanic and tectonic systems are chaotic and prone to sudden shifts. The current magma surge could dissipate without further consequence, or it could mark the beginning of a drawn-out episode of geological instability. Already, thermal features in Yellowstone, such as geysers, mudpots, and fumaroles, have shown altered behavior. Some geysers have erupted more frequently than usual, while others have gone silent. Gas emissions from fumaroles have increased in volume and changed in composition, indicating changes in the chemistry and depth of hydrothermal fluids. Increased seismic activity is perhaps the most ominous component of the alert. Earthquake swarms have intensified not only in number but in spatial distribution, suggesting that magma is not moving in a singular conduit. but instead branching outward, seeking paths of least resistance through the brittle crust. These swarms often cluster near known fault lines, raising the specter of triggered seismic events. If magma forces its way into a fault zone already primed for rupture, it could catalyze an earthquake powerful enough to damage infrastructure across state lines. Seismic sensors have already recorded tremors ranging between magnitude 3 and 4.7 in areas not accustomed to such frequent shaking. The geochemical data collected during this period of heightened activity have also fueled concern. Elevated levels of sulfur dioxide and carbon dioxide have been detected across monitoring sites, which typically signals that magma is nearing the surface. The gases are exsolving, separating from the molten rock, as pressure decreases during the magma's ascent. These gases can serve as precursors to eruptions and often accumulate rapidly in the final phases of magmatic movement. The correlation between increased gas emissions and the recorded thermal anomalies paints a picture of a complex, escalating process unfolding beneath the surface. Scientists have also noted changes in groundwater behavior. In Yellowstone and the surrounding areas, aquifers have shown signs of heating and expansion. Wells that once produced cool water now emit steam or abnormally hot water. Shallow lakes have exhibited sudden changes in temperature, and unusual algae blooms have begun to form, likely triggered by the chemical and thermal influx. These subtle but cumulative effects suggest that the magma's influence is reaching closer to the biosphere, affecting not only the geology, but the ecosystems that depend on it. Mount Rainier's glacial systems are under close observation due to the hazard posed by rapid melting. As magma intrudes closer to the base of the mountain, even slight increases in subglacial temperature can destabilize ice sheets and initiate meltwater flows. These can act as lubricants, reducing friction along the base of glaciers and accelerating their movement downslope. The real danger lies in the potential mixing of meltwater with volcanic material, forming deadly lahars. Historical evidence shows that Rainier has produced such flows in the past, burying entire landscapes. With towns like Ording and Puyallup situated in these ancient lahar paths, the current magma surge under Rainier raises alarms not just in scientific circles, but also in emergency management agencies. In the Tetons, the implications of magma movement are subtler but still profound. The structural integrity of the Teton Fault is under strain, and any additional pressure from below could trigger a cascade of geological consequences. Unlike Yellowstone or Rainier, the Tetons do not host a central volcano, but they are intricately linked to the Yellowstone hotspot system through deep lithospheric channels. These channels act like pressure valves or release points, and when one part of the system is disturbed, the rest can follow. The appearance of new fumaroles and rising ground temperatures at specific points in the Teton Valley support the notion of a broader subterranean reaction to the regional magma surge. This multi-site surge raises the specter of a domino effect where stress transferred from one volcanic center could catalyze activity in another. While not necessarily simultaneous eruptions, the interconnectedness of the region's geology means that stress, heat, and magma could migrate along structural weaknesses, triggering successive events over time. The possibility of a chain reaction, starting perhaps with seismic activity, followed by hydrothermal explosions, and culminating in a volcanic eruption, has made the situation a focal point of international geological interest. The instrumentation used to track these events has never been more advanced, allowing scientists to peer into the Earth's crust with unprecedented detail. Still, the data reveal a system on the brink of change rather than a precise forecast. Ground deformation is being monitored by GPS stations showing measurable uplift in several zones, while INSAR interferometric synthetic aperture radar provides time-lapse views of crustal movements. These tools, combined with deep borehole sensors and fiber optic strain gauges, indicate a pressure buildup across a region hundreds of miles in diameter. Perhaps most unsettling is the suddenness with which this red alert was declared. Geological change typically unfolds over centuries, yet the indicators in this case have shifted dramatically within weeks. This rapid evolution has unsettled long-held assumptions about the tempo of North American volcanic systems. It also suggests that Earth's deep processes may be more volatile and more synchronous than previously imagined. The situation is evolving, and geologists are working around the clock to refine their models and projections. Volcanic systems are capricious, and while this alert does not confirm that an eruption is imminent, it does establish a baseline for extreme vigilance. The priority now is observation. Meticulous, round-the-clock data collection to detect any acceleration in the system's behavior. As more information comes in, researchers hope to better understand the triggers and thresholds of these immense geological forces. This simultaneous activation across Yellowstone, Mount Rainier, and the Tetons represents a rare and powerful reminder of the deep forces that shape the planet. Beneath the surface beauty of geysers, snow-capped peaks, and alpine lakes lies a vast engine of molten rock and shifting tectonic plates. The magma surge and red alert status do not mark an ending, but rather an unfolding narrative in the ongoing story of Earth's dynamic crust. The red alert issued by geologists in response to the unprecedented magma surge beneath Yellowstone, Mount Rainier, and the Teton Range marks a rare confluence of geological signals, a moment when multiple volcanic and tectonic systems appear to awaken in tandem. Each of these regions, with their unique structural and geothermal profiles, is now demonstrating signs of internal agitation, forcing scientists to reevaluate long-held models of regional stability and volcanic dormancy. As sensors capture the deep murmurs of rising magma and tectonic strain, the implications grow more far-reaching, not just in terms of potential volcanic eruptions, but also in how this signals a broader transformation within Earth's interior processes. Beneath Yellowstone, the magma surge is not isolated to a single chamber. Instead, seismic tomography has revealed a sprawling, multi-tiered magma reservoir that lies beneath the park, with pockets of molten rock scattered through the lower and upper crust. The red alert was triggered in part by a dramatic increase in the rate of melt migration within these reservoirs. It's not just that magma is present, it's that it's moving, heating, and pressurizing new parts of the crust. The sudden rise in melt fraction, the percentage of rock that is in molten form, suggests that thermal energy is diffusing more aggressively than before. This has caused rocks to become ductile and deformable, increasing their likelihood of fracturing and creating new conduits for magma to ascend toward the surface. One particularly troubling development is the deep harmonic tremor activity that has been detected. These low-frequency seismic waves are often associated with the movement of magma through narrow pathways. Unlike typical earthquakes, which occur due to fault slippage, harmonic tremors resonate like a constant rumble, an underground roar indicating that molten rock is pushing through layers of crust with force and momentum. The presence of sustained harmonic tremors beneath all three regions is highly unusual and strongly indicates a common triggering mechanism, likely rooted in a broader mantle disturbance. At Mount Rainier, the situation takes on a different character. While Yellowstone's concern revolves around explosive caldera-style eruptions, Rainier poses the dual threat of lava and hydrological hazards. As magma intrudes into the roots of the volcano, the possibility of hydrothermal explosions increases. These occur when superheated groundwater flashes to steam, creating explosive blasts that eject rock and ash without a lava component. Recent anomalies in underground water temperature and pressure at Rainier's flanks have led geologists to fear that these violent steam-driven events may precede any magmatic eruption. The historic record supports this concern, with similar precursory events having been documented prior to significant volcanic episodes elsewhere in the Cascade Range. Meanwhile, the Tetons are presenting a case study in how magma movement can strain and destabilize fault systems. Remote sensing has captured a rare phenomenon known as slow-slip events occurring along the Teton Fault. These are subtle, silent shifts in the crust that redistribute tectonic stress without the jolts of conventional earthquakes. However, such shifts are often precursors to larger seismic events. The intrusion of magma may be lubricating faults or altering the stress field in a way that makes rupture more likely. What's more, gravity measurements taken from airborne platforms suggest mass redistributions in the crust beneath the Tetons, a strong sign that melt is pooling in new zones, weakening the structural integrity of overlying rock. The temporal alignment of these phenomena suggests more than coincidence. Many geophysicists now believe that what's happening is not a series of unrelated events, but a phase shift within the North American Plate's volcanic corridor. This corridor spans from the Snake River Plain through Yellowstone and arcs northwest toward the Cascades. For centuries, this corridor has been slowly pulsing with geothermal energy, but the recent red alert points to an acceleration. an upscaling of that pulse into something more immediate and potentially volatile. Understanding why this phase shift is happening now requires looking even deeper into Earth's mantle and the patterns of convection that shape it. Some experts propose that the plume-feeding Yellowstone is entering a new convective cycle, drawing more material upward from the deep mantle at a faster rate. This could explain the sudden pressure increases, temperature spikes, and expansion of melt zones beneath the surface. Furthermore, the mantle plume may not be a narrow column as once thought, but rather a wider, branching system that sends heat and molten rock toward multiple volcanic centers across a vast area. This concept redefines what it means to be a hotspot, suggesting a more distributed, interconnected network of thermal conduits under the western United States. Another emerging area of research is the role of lithospheric thinning in these events. As the crust stretches and becomes thinner in certain regions due to tectonic forces, it becomes more susceptible to penetration by rising magma. New measurements from magnetotelluric surveys, techniques that use natural electromagnetic signals to map underground conductivity, have revealed anomalously thin crust beneath parts of the Tetons and southern Yellowstone. These thin spots are effectively weak points where magma can breach more easily, and they might serve as breakout zones if pressure continues to build. The socioeconomic implications of this red alert cannot be overstated. Yellowstone, Rainier, and the Tetons draw millions of visitors annually. These regions are hubs for tourism, agriculture, and energy production. If this geological unrest intensifies, it could disrupt critical infrastructure, including transportation networks, water supplies, and power lines. Towns near Mount Rainier, like Enumclaw and Auburn, lie directly in the path of historic lahar flows. Meanwhile, Jackson Hole, nestled beside the Tetons, is not just a scenic resort area, but a vital node in the region's economy. Even a moderate eruption or seismic event could paralyze daily life, forcing evacuations and demanding rapid mobilization of emergency services. In Yellowstone, the proximity of magma to surface hydrothermal features raises unique ecological questions. The park's complex microbial ecosystems, which thrive in hot springs and geysers, are highly sensitive to changes in temperature and pH. If magma-induced shifts continue, entire biomes could be altered or eradicated. This would not only affect the natural balance, but also scientific research, as Yellowstone's microbial life holds keys to understanding extremophile biology and even the origins of life on Earth. The monitoring efforts have now intensified to a level not seen in decades. Drones equipped with thermal and gas sensors are flying daily missions across these regions. Ground-based teams are deploying portable seismometers, gas chromatographs, and thermal infrared cameras to fill in the gaps left by permanent installations. Satellite data from agencies like NASA and the European Space Agency are being cross-analyzed in real time, creating multi-layered maps of ground movement, heat flow, and gas dispersion. This flood of data is being fed into high-resolution models that simulate possible eruption scenarios, seismic sequences, and the cascading effects that could ripple outward. Public communication has also become a critical component of the response. The issuance of a red alert is not only a scientific benchmark, but a public safety measure. Local governments are holding daily briefings, while national agencies are working to update hazard maps and emergency protocols. Communities near Mount Rainier have resumed evacuation drills, while those near Yellowstone are being educated on what to expect should seismic or thermal activity intensify. The challenge is to inform without inciting panic, a delicate balancing act as the ground itself continues to shift. Scientists are also using this moment to advance the frontier of volcano forecasting. Traditional models rely heavily on surface observations and historical precedent, but these have limitations. The current situation presents an opportunity to refine AI-based forecasting tools that can process petabytes of real-time sensor data to detect hidden patterns and anticipate phase transitions in magmatic systems. These tools are still in development, but early results have shown promise in identifying subtle precursors to seismic swarms and magma chamber inflation. On an academic level, the simultaneous unrest beneath these major regions is reshaping the theoretical frameworks that underpin our understanding of continental volcanism. The simplistic division between isolated volcanic systems is giving way to a more nuanced view of a connected magmatic web. an intricate, interdependent system where energy and pressure can be transferred laterally across vast distances. This perspective may help explain not just current activity, but also past geological puzzles, such as why eruptions sometimes occur in unexpected places, or why seismic activity can jump from one range to another without an apparent direct cause. As data accumulates and models evolve, what remains clear is that the Earth's crust in the northwestern United States is under dynamic stress. The magma surge represents both a present threat and a long-term geological transformation. It reminds us that while these landscapes may appear timeless and serene on the surface, they are built upon molten foundations, always in motion, always changing. The red alert is more than a warning. It's a rare, visible flash of the Earth's deeper machinery, a moment when the slow processes of geology accelerate into human timescales, demanding attention, preparation, and above all, respect. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the magma surge? Do you expect an eruption soon? We want to hear from you. Thank you for watching and see you next time.